guess that's what friends are supposed to do. Oh yeah. Ooh, ooh. You can count on me 'cause I can count on you.
All right, let's go ahead and start by taking a look at this lecture survey question. So question says to consider a 2x2 Edgeworth box economy. Consumer A has strictly monotonic preferences over only good X and is otherwise indifferent about any level of good Y. Consumer B has strictly monotonic preferences over good Y and is otherwise indifferent about any level of good X. Consumers A and B have identical positive levels of each good endowed to them. And the question is, which of the following is true regarding this situation? And we have several different choices that are referencing the efficiency allocation properties of this Edgeworth box economy. Now, if A and B have identical levels of each good endowed to them, what must the shape of the Edgeworth box be? Let's start there before we do anything else. What does it have to look like? Yeah, that's right. It has to be a square, right? If everyone has equal allocations, that means each person has the same amount of X, same amount of Y. So we have this Edgeworth square box here where the endowment point is going to be smack where in that box? Yeah, that's right. It's going to be like right in the middle. Okay, so endowment point. Oops. Draw the box again. Here is our box. We have the endowment point right in the middle here. And let's call the origin in the bottom left A's origin. We'll call that OA. And the origin in the top right, we'll call B's origin OB. And let's think about this for a moment. If consumer A only cares about good X and doesn't care at all about good Y, what must consumer A's indifference curves look like? Right? No matter how much Y he's got, that would always leave him equally better off. If he only cares about X, then the indifference curves have to look how? What do you think? Yeah, they got to be straight lines. That's right. It's going to have to be a straight vertical line. Right? If you only care about good X, then that means this is going to be the better than direction, right? You only care about moving right. You don't care about moving up or down. Similarly, B also will have indifference curves that are straight lines, except since B only cares about Y, B's will look how? Yeah, that's right. B's have to be horizontal. Very good. So here's B's indifference curve. And again, the better direction for B is going to be straight down since B only cares about good Y, doesn't care at all about good X, which means we should very easily be able to identify the set of Pareto superior allocations relative to our endowment. And that would be in the yellow region. Okay, now intuitively, if you have someone that only cares about X and the other person only cares about Y, the efficient allocation, what should that really look like? If we're using the resources in the best way, one person only cares about X, the other person only cares about Y, then the efficient allocation, yeah, it's got to have them each getting only the good that they want. Okay, so I'm going to suggest there's actually only a single point in this diagram that identifies the efficient allocation, and that is in the bottom right corner. of the Edgeworth box. That's the only efficient allocation in the entire box. Okay, the farthest that A can go is all the way to the right. The farthest that B can go is all the way down, and they can't go any farther. We can't reallocate to make them any better off than they would be in that situation jointly. Okay, so the answer to this question is there is a single unique Pareto optimal allocation, meaning the core of the economy, right? That's the efficient allocations where both people are at least as well off relative to where they were in the endowment. That is also a single unique allocation. So if you got that one right here, nicely done. I think there may be a question in either the practice exams or the homework assignments, the problem sets that are very similar to this. So keep that in mind. And I know we didn't really talk about these types of indifference curves precisely, but you may have seen that in 100A, where they only care about one thing. They don't care about the other thing. They're just going to have a vertical or a horizontal indifference curve. So if you got that one right, nicely done. If not, no worries. Still getting your participation points. So make sure you're submitting those LSQs and LRPs prior to Sunday. We're going to pick up about where we had left off last class, continuing our discussion with respect to this general equilibrium framework that we have been working in. So our agenda is going to really pick up with our discussion of the pure exchange economy that we had started with in the last class segment. And we started thinking about introducing the role of prices into our Edgeworth box economy analysis. And what we're going to do today is we're going to introduce a concept known as the excess demand functions. So we can start thinking about, given a set of prices, okay, how can we figure out which prices would cause all of the markets to clear? And we're going to look at an important idea at the end of class today known as the Walras law, which I think is a very nice result that ties together this conceptual idea that the partial equilibrium approach kind of leaves some things out, but the general equilibrium approach allows us to analyze all of the markets simultaneously. And in this 2x2 Edgeworth box economy, we have two markets, the markets for goods X and Y. And at the end of the last class segment, we had introduced the role of prices into this situation, and we have recognized a slight difference relative to our Econ 100A treatment, where the right-hand side of this budget constraint was typically what we were thinking of as our income or our wealth. I'm going to abuse the term and use those interchangeably for now, since we're dealing with the static one-period model here. But in this model, right, we don't have just income endowed to the individuals anymore. The individuals are endowed with certain amounts of goods X and Y, and it's the market value of the endowment that really determined the value of how much the spending was constrained by the budget. So last class, we kind of rearranged the budget constraint. We solved for the y-axis variable. And we started recognizing, okay, we could see the usual slope of our budget constraint was the price of the good on the x-axis divided by the price of the good on the y-axis with the negative sign in front, which is very familiar. And then the vertical and horizontal intercepts were somewhat familiar, recognizing we had our income divided by the price of y, define the most y we could buy if we spent all of our income on y. And in the bottom right, we had income divided by the price of good x. And what we want to start thinking about here are the comparative statics of a price change in this environment. Okay, so given our budget constraint, and we know the following. We know the slope, we know our y-axis intercept, and we have our x-axis intercept here, which really characterizes the important elements of the comparative static analysis in the budget constraint. And without too much loss of generality, let's suppose the price of x goes up, okay, which is going to increase the ratio of px to py. Okay, what we want to do is think about all the effects this has on the elements of the budget line in our diagram. So if we have the increase in the numerator of the slope, okay, that's increasing the magnitude of the ratio of px to py, which I'm going to argue is going to increase the value along the y-axis intercept. That is going to go up. Okay. However, If we increase the price of X, you'll notice that's going to shift the X-intercept inwards, which I think is the few familiar aspects relative to 100A, is that shifts in. But notice the Y-axis intercept changes also. Okay, so we're not just getting the intercept where we change the price is the one that's changing. Actually, both intercepts do change here. And what we're going to observe is that the budget line actually gets a little steeper. Okay, meaning we're causing it to rotate not around the X or the Y axis, but we're causing the budget line to rotate around the endowment point here. If we were to think about the price of good X going down so that we have a reduction in that relative price ratio of PX over PY, then this process would work in reverse. We would have the Y-intercept shift inwards. We would have the X-intercept shift outwards. And again, we're getting a rotation around that endowment point, but in this particular case, it would be a counterclockwise rotation as opposed to a clockwise rotation. All right, so a little bit different comparative static content here. We don't have to worry about changing income in this example. We just have to think about changing prices because income, the value of our endowment, is determined by this relative set of prices. We could use exactly the same logic with respect to consumer B, so I'm not going to show B's budget constraint here. In fact, we're going to see in a moment when we plot the budget constraint in the Edgeworth box diagram, B's and A's budget constraint are really the same thing in that diagram, as we're going to see in just a moment. Now, before we do, let's go ahead and bring back our indifference curve so we can think more critically about what individual A would want to do if they faced the prices that gives them the budget constraint in red. And my question is, given this budget constraint, given these prices, will A want to hold on to their initial endowment, or will they want something else? What do you think of that? Is A going to want to keep their endowment point, or is their endowment point not an optimal choice for them? Okay, good. Some folks are saying not optimal because we don't have that tangency between the indifference curve and the budget constraint. I totally agree. Okay, so what we kind of want to think about here is, well, if consumer A did face those prices, consumer A's demand for good X and Y, right, how much they're going to choose in their utility maximizing solution, are different than what consumer A is endowed with. And I'm going to argue because of that, consumer A is going to want to reallocate. Okay, they're going to want a slightly different bundle than the bundle that they currently have. And you're probably already thinking to yourself, yeah, they're going to want a bundle that moves them down their budget constraint, right, until they do face that nice tangency between the indifference curve and the budget constraint, which means A is going to want to give up some good Y in exchange for good X. Okay, so we should be able to see here that given the endowment bundle, right, that is not optimal for what this consumer would actually want to demand, given the preferences implied by the indifference curve in that. Okay, so what we're going to do next is I'm going to think about implementing the budget constraint in the Edgeworth box diagram by thinking about B's picture and doing that flip around trick that we had introduced in the last segment so that we could look at this budget situation jointly for both of the agents at the same time in the Edgeworth box diagram here. Okay, so you'll notice once we incorporate prices, our red budget constraint here, it divides the Edgeworth box into two regions. Okay, there's the region in green here, which should look very familiar to us. That is the budget set for who? Yeah, that's right. That is the budget set for individual A. Okay, so we got consumer A's budget set. But you can recognize all that other space in the top right corner. That's the budget set from consumer B's perspective. So we can sort of see the prices divide the feasible region of the Edgeworth box into these two respective budget sets. And given both of these budget sets, we can think about the question, well, what would the utility maximizing solution actually be for each agent if they face those prices? And what we're going to see in a moment is neither A nor B wants to hang on to the original endowment point. The original endowment point is not optimal for either of them. Okay, so we're going to be able to think about setting up a trade through the market mechanism here, given this particular set of prices that the consumers would be trying to optimize against. Okay, so if we were to think about the optimal bundles for each consumer given the budget constraint, right, then we've just argued A is going to want to re-optimize, and B likely is also going to want to re-optimize given that we don't have a tangency. Okay, that's exactly what I'm getting at, Dylan. That's very good. They're both going to want to change relative to that endowment in order to move them closer to their points of tangency. Okay, now, are the points of tangency going to necessarily be equal? I'm going to argue that's going to depend really critically on the relative prices of goods X and Y. Okay, so let's take a look from consumer A's perspective here for a moment. If consumer A was really making their optimal choice, then we know they would be up on a higher indifference curve where they would face this tangency between the indifference curve and the budget constraint. So let's suppose for a moment that this indifference curve lets the individual A achieve a utility level of U star, in that this is the solution if they were to solve utility maximization against the prices that define the slope of the red budget constraint. Okay, so what we're looking at here, YA and XA, those are the demands for individual A when they're facing the current set of prices. Okay, notice we can compare those to the amount of good X and Y that individual A actually has, right? How much was A endowed with? Well, A was endowed with a little bit more Y than she wants, but A also is endowed with a little less X than she wants at the current prices. So we should see here, A is a little bit short of good X. So A wants more good X, but A's got a little bit too much of good Y. So A is going to want to give up some good Y in order to get more of that good X, which will be consistent with the utility maximizing solution for A at those given prices. We can make a very similar argument from individual B's perspective here. Okay. Given that red price line, B will also not stay at the endowment point. B will optimize until B's indifference curve is just tangent to that budget constraint. And let's refer to this utility level as U star for individual B. That defines B's optimal demand for goods X and Y, given their budget, given those prices. And we should be able to see that from B's perspective, B also is not choosing the old endowment point anymore. In fact, we can see here that B actually demands a little bit more Y than what B is endowed with, right? And B is also demanding a little bit less X than B is endowed with. So B looks like they're willing to give up some X here in order to get more of good Y. Okay, so I'm going to suggest that at the moment, the markets are not in equilibrium here. And here's how I'm going to make this argument. I'm going to bring both tangency points back, recognizing A wanted to choose a slightly different point than B wanted to choose. A's optimal bundle and B's optimal bundle are not the same. Okay? And because of that, Because of that, I'm going to argue the markets are not in equilibrium. So, yeah, I'm going to answer your question in just a second, Dylan. He's asking if they had equal amounts of good X and Y, would that mean they might not want to reallocate? And it really depends also on their preferences. I want to be clear about that. Three things: the preferences, the prices of the goods, and what they were endowed with. These things will jointly determine whether or not the individuals are going to want to reallocate. Okay, so what we should be able to see here is if we wanted to think about the total demand and the total supply in each market, the market for goods X and Y. Okay, well, if we look at the market for good X for a minute, we can see A demands XA, B demands XB, right? But do those demands actually take up the entire width of the Edgeworth box? Answer is what? And they don't. Okay, so we can see here that if we add up the total demand for X, the demand for X in total doesn't use up the full supply of X available. And so I'm going to argue that because of this, the market for good X must be in a surplus situation. There's more of its supply than these individuals are demanding at the current set of prices. Now, what about the market for good Y? Well, if we carefully look at the demands for Y, we're going to see almost the opposite situation, right? Here is A's demand for Y, right? Goes up to this yellow line. But notice B's demand for Y goes even further past that, indicating now that the total demand for good Y, okay, because we get that overlap, right? We don't not only exhaust Y, the total demand for Y is more than the supply available, meaning good Y is not in a surplus situation. It's actually a what? Yeah, it's going to be a shortage. It's exactly right. Very good. Okay, so we've made this argument here that because of this, right, these markets are not in equilibrium. And at the current set of prices, the total demand in each market is not equal to the total supply in each market, meaning the prices that are defining the budget line here are not equilibrium prices. If they were equilibrium prices, then the markets would be clearing. Supply would equal demand in those markets. So I'm suggesting they're not equilibrium prices, at least not the slope we have drawn in this picture yet. Okay, we recognize we got a surplus in the market for good X. We have a shortage in the market for good Y. And what I'm going to do now is I'm going to take a partial equilibrium snapshot of each of these markets. Okay, and we want to remember here again that X was in surplus and Y was in a shortage. Okay, so here is the picture, the partial equilibrium picture for good X. Okay, this is our pretty standard supply and demand picture that we use to think about modeling competitive markets. Notice there's a small difference, and instead of just the price of good X on the vertical axis, we're looking at really the relative prices of X compared to Y. Very small difference here. And so we're taking this partial equilibrium perspective, and we recognized already that in this market, we had an excess supply situation. We had a surplus, meaning the current price ratio had to be where relative to the equilibrium price ratio if there's a surplus. What's that tell us about the current price ratio? It's got to be 2 what? Yeah, it's got to be too high. Right? If we have a surplus where supply exceeds demand, I'm going to argue that current price ratio, right, is a little too high. Okay, that is why the market for good X is in a surplus. Okay, now, normally what happens if we were in our perfectly competitive market framework here, many buyers, many sellers, right? There's downward pressure on the price, right? That would kind of alleviate that excess supply situation. Okay. Now, let's shift gears and look at the market for good Y. In the market for good Y, we also argued was out of equilibrium, but not because there was a surplus. And again, notice in the market for good Y, I'm plotting PY on the vertical axis, but it's the ratio of PY to PX. Okay, in the market for good X, we had PX over PY was how we were thinking about the relative price of good X. But in the market for good Y, the relative price of Y is PY divided by PX. So again, taking this partial equilibrium approach here, given that we have a shortage in the market for good Y, what must be true about the actual price ratio relative to the equilibrium price ratio? Yeah, it's got to be lower than the equilibrium. Very good. Okay. Notice that current price ratio, the demand is much higher than the current supply, which is why we said this market was in a shortage from that general equilibrium perspective. Okay, so again, I'm going to suggest a shortage. In order to alleviate that means the price of Y is relatively low in this market. And back in our competitive market environment, right, the story was there will be upward pressure on that price. Okay, so the beautiful thing about general equilibrium is we don't have to just look at one market or another in isolation. We're actually looking at both of them together. And we're going to see something pretty cool happen. Hey, we're going to think about, well, what is the prices that would actually put us in an equilibrium? And we recognize, well, you know, we have PX over PY in the market for good X is the price of good X, but we have PY over PX in the market for good Y is the price of good Y. Hopefully you're looking and you're seeing, oh, those prices are just inverses of each other. In fact, if we were to lower the price in good X's market, what effect will that have at the same time in the market for good Y? Yeah, it's going to start to raise the price in the market for good Y. So we're going to see something kind of cool happen here. That as we try to adjust the prices to bring those markets into equilibrium, there is actually a price ratio that will cause both of these markets to be in equilibrium at the same time. Okay. We're going to do a small adjustment, and we're going to see as we adjust, both markets get pushed towards equilibrium together, and this is not a coincidence. And this is not a coincidence. So a couple takeaways here before we think about how can we figure out the price, right? And by the price, I really mean the ratio of the prices. Okay, what is the price ratio that would put us in an equilibrium where A's optimal bundle leaves exactly enough good left to account for B's optimal bundle so that all of the markets clear simultaneously? And so that's what we got to figure out here. Okay, what is the price level that is going to solve this multi-market clearing situation, right? Capturing the full interrelationship between all of the markets in our model. In this case, we got these two here. Okay, so a couple of takeaways at this point. we just recognized when one market was not in equilibrium, this corresponded to the other market also being nudged out of equilibrium. And we also noticed as one market adjusts towards equilibrium, that caused the relative price in the other market to also adjust towards equilibrium. And I'm going to suggest that in a very particular way, this result even generalizes to more than a two market situation, but we have to be a little careful about specifically how we describe it. Okay, the point is the following. At the current set of prices, right, to find the slope of that red budget line, okay, they're going to have to change in order to alleviate the pressures inherent in this disequilibrium situation. We recognize PX over PY has to go down to bring X into equilibrium, which is the same thing that would actually bring PY over PX up towards equilibrium. So we want to think about how can we figure out that optimal price ratio, optimal in the sense that it would leave us no shortage or no surplus in the aggregate across all of the markets in the economy. Okay. So in order to answer this question, we're going to introduce a somewhat novel concept known as the excess demand functions. So the question is it possible for one market can't reach equilibrium? But I'm not sure about your question there, Winnie. You might have to rewrite that. I think the answer you're going to see here is no in a second, but just think about it for a moment. I'm going to prove this result, and then you should be able to see the answer to your question yourself. It becomes, I think, very clear. Okay, so let's go ahead and talk about something called an excess demand function. Excess demand function is going to be very useful in terms of describing a shortage situation or a surplus for a given individual. Okay? And then we can add up these excess demands over the individuals to think about measuring the shortage or surplus for a particular good. For example, for individual I, we're going to define the excess demand function using the function Z. So Zi comma X is I's excess demand for good X. And the way we're going to calculate this is we're going to take the demand for good X minus the amount of X that you were endowed with. This is your demand minus your supply if you're individual I. And Xi, the demand, that is the Marshallian demand curve we get from solving the utility maximization problem. And so if I figured out the utility maximizing choice of X, and then we subtracted out how much of it I already have, that measures how much my demand is in excess of my endowment. Okay, similarly, we can do the same thing for good Y. Okay, we can take the demand for good Y that we find from solving our utility maximization problem in green here. And then we're subtracting out the amount we're endowed with as the individual I, which is Y bar. So this is measuring the extent to which individual I's demand for good Y exceeds the supply of good Y. If that's positive, we have an excess demand situation, right? We have a shortage. If that thing is negative, then we would have an excess supply situation. We would have a surplus. Okay, so these are the excess demands for an individual for the moment. Okay, now, if we had the individual excess demands, okay, I'm going to suggest we can add these up across the individuals to compute the total market excess demands. For example, in the market for good X, right, the total excess demand, I'll use the capital Z to refer to the market excess demand. We get that from just adding up the individual excess demands over the consumers in the market, which are defined just by consumers A and B in this case. Okay, so we would take the demand for A plus the demand for B, all for good X, minus the endowments of A and B's good X. Okay, and this will give us the total market excess demand function. And we can do the same thing for good Y. We can do exactly the same thing for good Y. Let's add up the excess demands for individuals A and B, but in the market for good Y. We're going to do that. Okay, which means we have to add up the difference between each person's demand and their endowment, and then we sum across the individuals. So we're getting the two individual demands minus the total endowment of Y, the total vertical distance of that Edgeworth box. Okay, so what I would like us to do next is go through an example where we're going to use some preferences to think about the demand functions from utility maximization. And then we're going to subtract out the endowments so we can get the excess demand functions for each individual for each good. And then we'll be able to add that up over the individuals to think about the market excess demand functions for each market X and market Y. All right, so let's go ahead and think about this situation that we've looked at before. We had this pure exchange economy where individual A was given 1 unit of X and 2 units of Y, and individual B was given 3 units of X and 1 unit of Y. Now the question is, given constant prices, we want to write out expressions for the consumer's budget constraints, and that's where we're going to start thinking about this. Okay, so consumer A's budget constraint, it will look like this. And all we have to do here is plug in consumer A's endowments for X and Y into those values. And then we will have consumer A's income on the right-hand side corresponding to her endowments. Similarly, for consumer B, we can write out the budget constraint and we can plug in consumer B's endowment of X and Y. So we can write out consumer B's budget constraint more precisely. Okay, so we have the budget constraints. Okay, we also have the preferences for these individuals. So if you have the preferences and you have the budget constraints, you should be able to solve the utility maximization problem, which you had done extensively in Econ 100A. All right, so I'm going to take a little bit of a liberty with that knowledge, okay, and assume that we remember, if we have a Cobb-Douglas function and we solve that problem, what those demands will look like. Okay, but what I would like us to do is figure out the excess demand functions for these two consumers. Okay, there's going to be 2 for each consumer, 1 for each good. And if you had solved the utility maximization problem for these particular form of the Cobb-Douglas preferences, maybe you remember that if you were endowed with some income value I, you would get I over 2px as the demand for good X. You get I over 2py as the demand for good Y, but we don't have income in this model. Right? We don't have an I. Instead of I, okay, what can I plug in for income? We don't have I. We should be plugging in what for I? Yeah, it's going to be the value of the endowments. That's right. We're going to plug in the X bar, the Y bar values for our income. So hopefully remember that consumer A was endowed with 1 unit of X and 2 units of Y. So A's income would be PX plus 2PY, and all we're going to do is plug that in for the income value in the Marshallian demand function. And that then will give us the Marshallian demand curves for goods X and Y for this particular individual, for individual A. Okay. Notice I've simplified them a little bit. And I've done this purposefully so that we could see the price ratio pop out here. Everybody see that price ratio popping out there? PX over PY to the -1. I've done that deliberately. Okay, the demand for good Y looks a little bit different. A little bit different. Okay, but again, we've made that price ratio pretty visible. There it is, PX over PY. Okay, so if you give me a particular price ratio, I can plug that in and tell you exactly how much A will demand of each good. Okay, in order to find A's excess demand function, all we're going to have to do with each of these demands is subtract out what? Yeah, that's right. We're going to just subtract out the endowments of those goods. Okay. So let me clear my annotations here. So all we're going to do is take XA and subtract X bar A in order to get the excess demand for good A for good X for individual A. Okay, now what was X bar A? It was 1 unit. So all we have to do is take the demand, subtract that endowment, and now we have the excess demand function for good A. Okay, and this is for individual X. Similarly, A's excess demand for good Y, we're going to take their demand and subtract out the endowment, which was 2 units of good Y. And we can simplify that a little bit here, right? We get 1/2 PX over PY minus 1. Okay, so what we have done here is we found the excess demand function for good A for individual X, for good X for individual A, and we found the excess demand function for good Y for individual A. Let's do the same thing for individual B. Now remember, B had the same preferences, which means the demand functions will look the same, but B's endowments were a little different than A's. B had 3 units of X and 1 unit of Y endowed. So B's income in the pink box is different than A's income. So if we plug that value in for the income function in those demand curves, okay, which again, those demand curves on the right came from solving budget constrained utility maximization. This will yield the following Marshallian demand functions for individual B. Okay, notice again, we've made the price ratio pretty visible here. It's a good idea to write this in terms of PX over PY. Okay, same thing also for Y's, good Y's excess demand for individual B. Okay, I've made that price ratio visible because in a moment, we're going to want to solve for the price ratio. So that's why I've kind of brought it with me like this. We're going to figure out what is the value of that thing that's going to clear all of the markets at the same time. All right, so all we need to do to find B's excess demand functions is to subtract out B's endowment from each of those Marshallian demands, just like we had done for individual A. So if we take B's demand for good X and we subtract out B's endowment of good X, right, which was 3 units of good X endowed, and so X bar going to be 3 here. Okay, then we can figure out the expression for B's excess demand function for good X. B's excess demand for good X is 1/2 PX PY to the -1 power minus 3/2. Okay, so you can see if PX over PY goes up, that drives the excess demand for X down. B's excess demand for good X is just Y's, the demand for Y for individual B minus B's endowment of good Y, which was only 1 unit in this case. So again, we have now arrived at individual B's excess demand functions for both good X and good Y. Okay, so we solve utility max, right? To get the demand functions, we subtract the endowments, and that leaves us with the excess demand functions. Here we have A's excess demand functions on the left side of the screen. We have B's excess demand functions on the right side of the screen. Now, what we want to do is figure out the total market excess demands in each segment. So what we're going to have to do here is we're going to have to add up all of the demands for good X. That'll give us the total excess demand for good X. And we'll do the same thing by adding up the excess demands for good Y to figure out the total market demand, right? Total market excess demand for good Y. Okay. So all we're going to do is aggregate those values as I've just described. Okay. So we're going to add up the demand for X for individuals A and B. And then we're going to go ahead and we'll add up the demand functions, the excess demand functions, that is, for good Y for individuals A and B. Okay. And if we do that for good X, and we're fairly careful about what we're doing, let's just point this there. This one goes here. And here's what we wind up with. We now have the aggregate excess demand function for the market for good X. If we want good X to be in equilibrium, then we need the term in the blue box here to be equal to what? Yeah, it needs to be 0. That's right, Winnie. Very good. Hey, if we add up the demands for good Y, a similar idea here, right? A's demand goes in here, B's demand goes in there. Then we can compute the total excess demand in the market for good Y. And if you look carefully at the term in the light blue box, if we want the market for good Y to be in equilibrium, then the term in the light blue box has to also be 0. Okay, so what we need to do here is kind of solve an equation for Px over Py, right? Or in terms of Px over Py, that would make both of those terms in the blue box 0 at the same time. Okay, that's going to be the task at hand. All right, now before we actually go through an example and do that, let me introduce an important result here known as the Walras law. The really critical feature we've recognized that separates the general equilibrium framework apart from the partial equilibrium framework is that it captures the interrelatedness of all of the markets at once in the model. Okay, so we're going to show an important feature of this general equilibrium framework. And this feature is if one of the markets is out of equilibrium, then another one will be out of equilibrium. In the case of our 2 market situation, we've already seen this. The market for X, right, was in a surplus, and at the same time, the market for Y was in a shortage. And that was not a coincidence. If there's a surplus in one market, right, meaning we have a negative excess demand in that market, there's going to be a shortage in the other market, meaning we have positive excess demand in the other market. And what we're going to see here is if one market is in equilibrium and we only have one other market, then the other market will also be in equilibrium. And we can fairly easily generalize this result to more markets, but we have to be a little careful about how we interpret that. Okay, the 2 market case is very special because there's only 2, one and the other. But if you have 3 markets, then the result is a little different in how it generalizes, but it generalizes in still an important way. So what I want to do here is I want to prove this for our Edgeworth box economy that we've been dealing with. And I'm going to prove it in a very general sense. Okay. Let's begin by assuming that each agent satisfies their budget constraint. Each agent is abiding by their budget constraint. And if they have monotonic preferences, we know from 100A that expenditure should exactly equal or use up their whole budget. What I'm going to do next is I'm going to add both constraints together. Just add them up vertically. So the right-hand side would be the total value of the endowments across the individuals. The left-hand side would be the total expenditure of the individuals. And then we should also recognize on the right-hand side, XA bar plus XB bar, that's the total endowment of X, just like YA bar plus YB bar is the total endowment of Y. And then what I'm going to do is I'm going to subtract everything to the left and factor out all the terms that involve a price being multiplied by them. Okay, now I want you to look very carefully at the terms in pink and purple in the bottom line. What does the term in pink have to be? How will we interpret that? The term in pink, what is that? Yeah, it's the excess demand for good X. Similarly, the term in the purple, that's the excess demand for good Y. So if the budget constraints hold, this condition has to be true here. Okay? And we got to think about how to interpret this condition. The left-hand side of this equation in the green box, that is the total value of the excess demands added up across all of the markets. And this is telling us that the total value of the excess demands at any time has to always equal 0. Okay. So I'm going to suggest this is a really important result for us to understand. Okay, we've showed that as long as the budget constraints hold, this condition in the green, Walras law, has to be true. Now, what do we know is true about the value of prices, PX and PY? What type of values should those be? PX and PY. Yeah, they should be positive. PX and PY are both prices, so they're not going to be negative. They're not going to be 0 either. But the excess demands, they could be positive, they could be negative, they could be 0. Right? If the excess demand is positive, that means you have a shortage. If the excess demand is negative, that means you have a surplus. And if the excess demand is 0, that means what? It means we must be in equilibrium. That's right. Now, if you look at this carefully, let's suppose for a minute that the market for good X is in equilibrium, meaning ZX is equal to 0. If the market for good X is in equilibrium, what has to be true about ZY? If I plug in a 0 for ZX, I get PY times ZY equals 0, which means ZY must what? Yeah, gotta be 0. Okay, so if the market for X is in equilibrium, that implies that Y's market also will be in equilibrium. Okay, so it's not that we're going to put one market in equilibrium and then the other one won't be in equilibrium. That actually can't happen. Okay, that cannot happen here. Okay, conversely, if Y is in equilibrium, then X has to also be in equilibrium. Okay, and that's going to simplify our life quite a bit, because instead of me having to worry about solving each market equilibrium separately, I only have to worry about putting how many markets in equilibrium here. Yeah, just one. If one of the markets is in equilibrium, then both of them will be. If we had, instead of two markets, suppose we had n markets, then the result generalizes in the following way. If n minus one of those markets were in equilibrium, then so is the last market. If I have three markets, that means if two of them are in equilibrium, then so is the third. Okay. The other way we can think about this is if the market for X has a surplus, right? So that ZX is negative. That means the market for Y has to be in the opposite situation. It has to be in a shortage. Okay. Conversely, if Y is in a surplus situation, then that means the market for X will have to be in a shortage situation, a positive excess demand situation. Okay. So this Walras law, the implications are, if I have two markets, if one of them is clearing in equilibrium, so is the other. If one is out of equilibrium, so is the other. Okay. If we have more than two markets, if one of them is out of equilibrium, then at least one other market must be out of equilibrium. But if n minus one markets are in equilibrium, then all of them have to be in equilibrium. Yeah, that's right. So if you had three markets and two of them were in equilibrium, that would guarantee that the third one would have to be in equilibrium as well. That is correct. So let's go ahead and look at our excess demand functions. Okay. And then we're going to work through that example we kind of were dealing with a moment ago where we had those Cobb-Douglas preferences, and we're going to figure out what is the price set, what is the ratio of prices that would simultaneously put both of those markets in equilibrium, meaning the consumers do what's selfishly optimal for them, and that winds up clearing all of the markets using all of the resources exactly. Okay, so we had the budget constraints before, right? We rewrote this, okay? And what I want you to notice about the budget constraint now is if we were to double all the prices, if we scaled all the prices by the same factor, I'm going to argue this would have to leave the budget constraint as I've defined it above, unchanged. It would have to be unchanged, right? Because if I double all the prices, then the value of my income will also double, because that's just the endowment valued at the prices. Okay, meaning the budget constraint is homogeneous of what degree? Yeah, it's HD0. Very good. It is homogeneous of degree 0. Okay, so if we doubled all the prices, right, and our income doubles and we solve the utility maximization problem, that means our budget set has not changed. Okay, so the Marshallian demands would remain the same. Okay. You hopefully recall this result from Econ 100A, that the Marshallian demand functions were homogeneous of degree 0 in income and prices. Okay, we're seeing the same thing here. Now, I'm going to argue that this result also spills over into the excess demand functions. Okay, because the Marshallian demand functions, in this case, are also going to be homogeneous of degree 0. Because our budget sets don't change when we scale all the prices the same way, the optimal solution to utility max isn't going to change either. Now, the excess demands for each consumer were just the demands minus the endowment. And we'll consider here just the case for good X. It applies equally for good Y. So I won't show this for good Y. But it's got to be the case that because the Marshallian demands are homogeneous of degree 0, the excess demand functions have to be as well. If you doubled all the prices, it doesn't change your demand, doesn't change your endowment, which means your excess demand would be exactly what it was at the original set of prices. And the exact same argument applies to good Y as well. Okay, so the excess demand functions, they are homogeneous of degree 0, just like the Marshallian demand functions are. Okay, this argument carries over into the market excess demand functions as well. If I scale up all the prices, given that each of the individual excess demand functions was homogeneous of degree 0, then the market excess demand function must be as well. And the same idea applies for good Y. Okay, so we've proven here that not only are the individual excess demand functions homogeneous of degree 0, but so are the aggregate excess demand functions. Now, back to our disequilibrium situation. All right, we were looking at this, we recognized, hey, A's demand and B's demand were choosing different points in the box. That meant we weren't utilizing all of one resource and we were overutilizing another, right? One market was in excess demand, the other was in excess supply. And we saw that the market for good X, we had a surplus, and the market for good Y, we had a shortage. And what we're going to be able to do here is think about solving for the price ratio now, right? That we know Walras' law, that will simultaneously put both of those markets in equilibrium. Okay. And looking at this picture, right, we said PX over PY has got to go down, right? That'll bring PY over PX up in the right-hand picture. If we want PX over PY to go down, how is that going to change the slope of the red line in this picture? How's that slope going to change if we want PX over PY to get smaller? Yeah, I like what you're saying, Dylan. It is going to get flatter. And it's going to rotate around which point? Yeah, it rotates around that endowment point. Very good. Okay, so we're going to think about doing this. Let's rotate that budget line a little bit counterclockwise so it gets a little flatter. Right, that'll reduce PX over PY, which is the same thing as increasing PY over PX. And I'm going to suggest that that will alleviate both of those pressures in each market at the same time, the shortage and the surplus. And this is going to cause that budget line through the endowment to get a little flatter. And you'll notice when that line gets flatter, A and B will not want to choose the same bundles anymore. In fact, I'm going to argue if we choose the right set of prices, then what is going to happen is the point that A had chose and the point that B had chosen will move closer to each other. And our goal is to change those prices until they become exactly the same point in the Edgeworth box diagram, meaning neither good is in shortage and neither good is in surplus. Okay, so that is the goal. We're going to tilt that thing, and then we're going to look at the consumers reoptimizing. Everybody see here, they reoptimize a little bit at the new price line. Not exactly the same indifference curves. At that new flatter price line, I'm arguing now the demand bundle that A would choose and the demand bundle that B would choose are now the same point in that Edgeworth box, meaning the markets for both goods, X and Y, are clearing together. Okay, there was no shortage, right? No excess supply in either market. There is no surplus. Sorry, I have these words reversed. The excess supply here and excess demand, those should be switched, right? A shortage is an excess demand situation and a surplus is an excess supply situation. I apologize about that small typo, but we should see, despite that, the endowment is fully utilized here, right? A uses that fraction of it. B uses all the way the remaining amount of X, right? Similarly, A uses this much Y, and B uses exactly the amount of Y, demands exactly the amount of Y remaining in the Edgeworth box here. So I'm going to suggest that graphically, what we are looking at here is a competitive equilibrium allocation. And the way we're going to define a competitive equilibrium allocation for our 2x2 pure exchange economy is that given a set of prices, PX and PY, all of the consumers are maximizing their utilities subject to their budget constraints. They're each being individually self-motivated. And given that set of prices, both markets are clearing. There is no shortage. There is no surplus. Okay, so we went from being out of equilibrium to adjusting to being in equilibrium at this new optimal price ratio. Okay, optimal in the sense that it cleared both the markets. Okay, so the definition of the competitive equilibrium formally here for our 2x2 pure exchange economy, a competitive equilibrium has two parts to it. There is an allocation and a set of prices. We have an allocation and a set of prices such that taking the prices as fixed, each consumer is able to solve their utility maximization problem. Okay. And in the solution to that problem for all of the consumers, when we add up that behavior, all of the markets clear so that the excess demands in every market are equal to zero. So what I would like to do to wrap up tonight is to look at the numerical example we've been working through, and I'm going to solve for the competitive equilibrium allocation. Okay, so jumping back to our pure exchange economy when we had these two consumers, right? A had 1 unit of X endowed, 2 units of Y. B had 3 units of X, 1 unit of Y. They both had identical Cobb-Douglas preferences. And what we want to think about is checking things like, hey, at a given set of prices, are the markets in equilibrium or not? And the way we can verify this very easily is by looking at the aggregate excess demand functions for each market. Okay, if I plug those prices into the demand, right, the aggregate excess demand curve for good X, is the market for good X at equilibrium at that particular set of prices? Good, it is not. Right, you get 3 halves minus 2 is negative 1/2, not going to be in equilibrium. Okay, what about in the market for good Y? Also not in equilibrium. Okay, the excess demand for good Y would be positive 1/2 at those prices. Okay, so all we had to do here is plug in the price to see that the excess demands were not equal to 0. They were not in equilibrium. Now, if we wanted to find the equilibrium price, okay, I'm going to suggest that we can use Walras' law here to our advantage. Which excess demand function do we need to set equal to 0? The answer is what? Yeah, any one of them will work. Okay, so let's suppose here, right, we want to find the price ratio that clears both markets. So given the dependence between both markets, right, that ripple effect, we know we only need one of those markets to clear. So if I just take, for example, the excess demand function for good X, and I set it equal to 0, and I solve for the price ratio, that price ratio will also clear the other market. So let's go ahead and just verify this claim before we get out of here. Okay. If we do this for good X, we set the excess demand for good X equal to 0. And then I add the 2 over. And I can multiply by 2/3 and then flip some things upside down. And we should find that the set of prices that clears the market, right? What is the ratio of PX to PY that will do that for us here? Yeah, that's right. It is exactly 3/4. Okay, you should recognize if we plug 3/4 in for the price ratio here, okay, then that price ratio will also cause the market for good Y to clear as well. So we could have used either Y's excess demand function or X's excess demand function to figure out the set of market clearing prices for this general equilibrium pure exchange economy. With that being said, I think this is the appropriate place for us to wrap things up. So no class next week. Next week is a null week, other than the quiz coming on Monday. You'll have a quiz Monday, and then you're on your Thanksgiving break. No quiz the Monday following Thanksgiving on the 29th. That'll be week 10. We'll come back. You don't have a quiz that Monday, but there will be the 10th quiz during the final exam session as scheduled by the registrar. So if you have any questions, feel free to drop them in the chat. Do a little bit of rapid fire Q&A, but otherwise you are free to go. Have a wonderful evening, a wonderful weekend, and most importantly, a wonderful Thanksgiving break if I don't hear from you between now and then. Take care.